Chapter 18, Preparation for the Cycle. As we learned in Chapter 16, the pyruvate produced by glycolysis can have several fates. In the absence of oxygen, it converts to lactic acid or ethanol. In the presence of oxygen, it's converted into a molecule called acetyl-coenzyme A, acetyl-CoA, that is able to enter the citric acid cycle. The path that the pyruvate takes depends on the energy needs of the cell and the oxygen availability. In most tissue, pyruvate is processed aerobically because oxygen is readily available. For instance, in resting human muscles, most of pyruvate is processed aerobically by first being converted into acetyl-CoA. However, in very active muscle, much of the pyruvate is processed to lactate because the oxygen supply cannot meet the oxygen demand. Let's look at the big picture again. Where chapter 18 is here. That's the little arrow from pyruvate to acetyl-CoA. Let's look at another big picture. In this photo, the white area is cytoplasm in the cell. The orange area is mitochondria. In cytoplasm, glucose undergoes glycolysis, produce pyruvate, transport into mitochondria, and the pyruvate in the mitochondria can have two fates. One is being carboxylated to oxaloacetate, then undergoes gluconeogenesis, or oxidized into acetyl-CoA, then enter the citric acid, produce ATP. Chapter 18 is going to have two sections. Section 1, pyruvate dehydrogenase forms acetyl-CoA from pyruvate. Section 2, the pyruvate dehydrogenase complex is regulated by two mechanisms. Let's see another big picture. The glucose undergoes glycolysis, produce pyruvate, and then converted to acetyl-CoA. In that process, from pyruvate to acetyl-CoA, one carbon is lost in the form of a carbon dioxide, and two electrons are produced. The acetyl-CoA will continue, goes into the citric acid cycle, and two carbon dioxides will be produced. 8 electrons will be produced and generate ATP. Under aerobic condition, pyruvate enters the mitochondria, where it's converted into acetyl-CoA. The acetyl-CoA is the fuel for the citric acid cycle. The chapter 18 is about from pyruvate to acetyl-CoA and produce 2 electrons. That's the chapter 18. In chapter 19, we're going to study the citric acid cycle, where acetyl-CoA is oxidized to 2 carbon dioxide, produce 6 electrons, and another 2 electrons, 6 electrons from NADH, 2 electrons from 1 FADH2, and produce 1 ATP. Acetyl-CoA is the active carrier of acyl group. Acetyl-CoA is the fuel for the citric acid cycle. It's formed by the pyruvate dehydrogenase complex. This is the structure of acetyl-CoA. You can see the acetyl function group is at one end, and this acetyl unit undergoes a citric acid cycle, produce high transfer potential electrons, and ATP. Chapter 18 is a pyruvate turned to acetyl-CoA, produce 2 electrons. Chapter 19 is acetyl-CoA, produce ATP and high transfer potential electrons. 6 of them are from NADH, 2 of them is from FADH2. Among these 2 reaction equations, CoA as an enzyme, it involving in this pathway, but at the end it regenerate, and overall it doesn't show up in the equation. It cancels out. The pyruvate dehydrogenase complex is a mitochondrial matrix enzyme. Oxidatively decarboxylate pyruvate to form acetyl-CoA. This reaction is a irreversible link between glycolysis and the citric acid cycle. The equation is from pyruvate, 1 pyruvate with CoA plus NAD plus to form acetyl-CoA plus carbon dioxide, and 1 NADH plus a proton. This is a review of the mitochondria. The chapter 18 pyruvate converted to CoA, acetyl-CoA is inside the mitochondria. This is a photo of a mitochondria. The synthesis of acetyl-CoA from pyruvate requires 3 enzymes and 5 coenzymes. The synthesis of acetyl-CoA from pyruvate consists of 3 steps. The first step is a decarboxylation step, which pyruvate from 3 carbon to 2 carbon compound. And then second step is the oxidation, loss a pair of electrons, and then transfer to CoA to form acetyl-CoA. Pyruvate dehydrogenase is a complex, consists of 3 enzymes, and the abbreviation of the 3 enzymes is E1, E2, E3. We can see the prosthetic group are TPP, lipoamide, and FAD. We only introduce briefly about this TPP. It's a thiamine pyrophosphate. It's derived from vitamin thiamine, which is a vitamin B1. From this figure, we can see the 3 enzymes of the pyruvate dehydrogenase complex are structurally integrated, and the amide arm allows rapid movement of substrates and products from one active site of the complex to another. The formation of acetyl-CoA from pyruvate is irreversible in animal cell. The acetyl-CoA has two principal fates. One is metabolized by the citric acid cycle. Another one is incorporation into fatty acids. And we're going to talk about the acetyl-CoA metabolism by citric acid cycle converted to carbon dioxide in chapter 19. Pyruvate dehydrogenase complex is regulated by two mechanisms. The first mechanism is through enzyme E1 is a key site of regulation. A kinase, which is a phosphorylate the compound, inactivates E1. A phosphatase, which remove phosphate and activated the enzyme. Mechanism 2, the pyruvate dehydrogenase complex is also regulated by energy charge. ATP, acetyl-CoA, and NADH inhibit the complex. ADP and pyruvate stimulate the complex. This chart explains the first mechanism that regulated by enzyme E1. A kinase inactivates E1. A phosphatase activates E1. In mechanism 2, the enzyme complex is also regulated by energy charge. At high energy charge, with ATP concentration is high, you can see the ATP, high in concentration ATP inhibit the process. Also, the coenzyme A and NADH inhibit the process. At low energy charge, when ADP is high, ATP is low energy, ADP is high, then the process is stimulated. Basically, we can understand that all the products, ATP, acetyl-CoA, and NADH, inhibit the process. All the reactants stimulate the process, meaning when you have a high concentration of a reactant, yes, is the reaction move forward, stimulate the process, and when the product's concentration is high, then it inhibit the reaction moving forward. Clinical insights. Defective regulation of pyruvate dehydrogenase results in lactic acidosis. And the inhibits of the pyruvate dehydrogenase complex prevent the path the pyruvate goes to acetyl-CoA, and subconsciously pyruvate turn to lactate, which can result in lactic acidosis, which is the toxic acid environment. The production of a lactate in the presence of oxygen is a characteristic of cancer cell. We can review the Weber effect to understand this. This is another disruption of pyruvate metabolism. It's the cause of beriberi. insufficient PDH complex caused by thiamine deficiency result in insufficient pyruvate dehydrogenase activity, and it can cause beriberi disease. The vitamin thiamine is found in brown rice, but not in white rice. Arsenite poisoning is caused by arsenite inhibits the pyruvate dehydrogenase complex.